Hello everyone, my name is Vinh, and today I'm going to present the result that we submitted to the EAI Broadnest with the title Topology-Aware Scheduling Strategy for Distributed Stream Computing System. So we first talk about the related works and then the problem statement. Also, we'll talk about the TS stream in detail, and finally the performance evaluation. So in big data computing, there are two major sectors. The first one is batch computing, and the second one is stream computing. For stream computing, there are many of the aspects that the existing works gives you look at. For example, we have task scheduling, communication saving, latency saving, topology aware, and the graph partition. So as you can see here, the solution that we propose, namely TS stream, cover all these aspects that I just mentioned. So we propose a solution for task scheduling, which is capable of saving the communication resource with low latency and topology awareness. And all of these is based on the graph partition algorithm that we will describe shortly. The goals of TS stream is to reduce the latency in distributed stream computing system. We use a directed acyclic graph partitioning algorithm based on Laplace approach to get the good partitioning result. We also propose a strategy to allocate tasks to reduce the system latency. About the problem statement, here you can see this is a typical directed acyclic graph based on storm. You can see some of the storm terminology here, such as spout and bolts. You can refer to the paper for more detail about this. But basically, based on this DAC model, we define two metrics. The first one is the data transfer rate between the vertices or the nodes. We use this to define the latency of the system. And the second one is the resource consumed by the topology. So based on these two metrics, we design a communication model, and actually in the DAC computing graph, we usually have three types of communication overhead. The first type is the communication overhead between the computing nodes. The second one is the communication overhead within a compute node. And the final one is between the threads within a process. So the third type of communication overhead is actually less significant than the top two. So we will ignore the inter-thread communication, which is the final one, and focus on solving the first two communication overhead. So the idea is to group the nodes with high communication rate together to reduce the latency and the systems and increase the system's throughput. Now, let's talk about the TS stream in detail. So overall, a TS stream is a task scheduling strategy based on the topology awareness. TS stream can be used to reduce the latency and energy consumption of the system. And like I mentioned before, the solution is based on the Laplacian-based graph partitioning approach. In terms of system architecture, our solution provide 3 new modules to a standard storm stream computing system. Um, so they are monitoring module, database module, and the TS stream scheduling module. So as you can see here, we still have the basic component of the storm streaming system like the Nimbus, um, Zookeeper, the worker node, and supervisor, etc. The 3 new components that we add in here is the TS stream with the graph partitioning algorithm, a database, and the monitor module. The monitor module play an important part of the solution. It will watch the um, latency and the um, computing resource of the entire system, and it will use that to information to adjust the schedule through the TS stream graph partitioning algorithm. And the core of our solution is the graph division or graph partition based on Laplacian approach. Um, and this is to demonstrate what a good and bad division of a directed acyclic graph, when we can achieve this by using the Laplacian matrix. This is the algorithm, and you can refer to the paper for more detail. Now let's talk about the performance evaluation. We have the solution deployed on the system with 9 nodes. We have 1 Nimbus node, 2 Zookeeper nodes, and 6 supervisor nodes. We will not go into the system specification in detail. We focus on the performance result here. So we test the solution with 2 classic tasks. They are word count and top end, and we look at the system latency and the system throughput. So as you can see here, our solution achieves lower latency as compared to the standard TS stream with the word count. Also for top end, we achieve a better result for system latency. For system throughput, again, we have better performance for the word count and also for the top end tasks. So in conclusion, you can see that our solution achieve better performance in terms of system throughput and latency as compared to the standard storm default policy. But we will not stop here. As part of future work, we will focus on 2 main areas. So we will try to consider other system resource and then combine it with the state of the deck to reduce the delay of the system. The second area could be to deploy the TS stream in the real-world big data streaming environment, such as the real-time stock market analysis or embedded advertising to test our solution in the actual environment. Thank you.